Good morning, good afternoon, or good evening, depending on where you are in the world. Thank you for joining the webinar. Welcome to the Shields Up Session 9. This is Secure MPU Boot for an Insecure World. This is part of a three-part series in which we show how to secure your MPU designs. My name is Rick Dudley from the MPU Business Unit. I'm responsible for business development of the Americas and global MPU security marketing. This session should last about 20 minutes with a 10-minute question and answer at the end of the presentation. Security is a broad, wide, deep subject. Here we're focusing on what it takes to secure your hardware at boot time. So you want security, what do you want to protect? Determining what you want to protect will determine what type of security you're going to need or want. At each level of the product ownership, you have different requirements for security. The system suppliers, the service providers, and the end users, each of these have different security concerns. The system supplier may be worried about the brand name or his intellectual property, whereas the service provider wants to guarantee the data that he collects is protected, correct, and hasn't been tampered with. End users, of course, are always concerned about their personal data as well as their identity and protection of their identity. This leads to what critical functions and what kinds of data do you want to protect. Today we'll discuss why, the what, and the how of a secure boot process. As discussed on the previous slides, the why of secure boot is also part of the explanation of what do you expect to protect. By having a secure boot, the hardware has in place a hardware root of trust that can be built upon to build a complete and overarching secure system. Secure boot prevents the unauthorization of running applications in the equipment. It enables the loading of trusted applications and allows for trusted execution of the applications. This is done by checking the integrity of the application before deciphering and execution. Secure boot is only the second step in the process in providing the initialization of the hardware root of trust. What is secure boot? Secure boot is an interesting term. Is secure boot the only security needed for products? The simple answer there is no. Securing a boot process is only the middle step in the security journey. Secure boot assures that what is to be executed hasn't been modified, tampered with. Secure boot has a number of processes that make it secure and allow for secure operations of the equipment and products. The secure boot, the root of trust, is for the entire life cycle of the product, including all future updates and additional security update requirements. As discussed before, secure boot is the root of trust, with secure boot providing the authentication of the boot image and the boot files before decryption. Once the encrypted boot file has been authenticated, the images are then decrypted and placed in internal memory, and the bootstrap is then started, furthering the boot process along. Secure boot uses a number of functions in the device, like the boot ROM code, which is executed by the processor, which is the initial process of the starting of the boot. The processor looks for a valid image. If it finds it, an authenticated image, it will continue to decrypt into internal memory. If no image is found, it will go into a provisional loop, looking for the provisioning tool. Other resources used by the boot ROM are the key fuses, secured internal memory, HMAC, CMAC, hashing, AES decryption, and non-volatile memory, where the encrypted bootstrap and application reside. Once a valid boot image is detected by the boot ROM, the JTAG port is locked, ROM access is disabled, and the fuse access is disabled. Now let's walk through the process of booting up in secure mode. The system starts out with an encrypted image of the bootstrap and an encrypted image of the application in non-volatile memory as provisioned by the secure provisioning tool. The bootstrap image is encrypted with the customer key that is also derived of the secure ROM key and the customer supplied key. The application key is also derived from the customer key and is part of the bootstrap operation, as we'll see in a furthering slide. The ROM code accesses the non-volatile memory, looking for a valid encrypted image of the Bootstrap. The image is validated using the hash engine and the customer key in the OTP fuses. The ROM code then moves the encrypted Bootstrap image into the non-volatile, from the non-volatile memory into SRAM, still encrypted. The boot ROM then decrypts and rewrites the decrypted Bootstrap image into internal memory and authenticates the Bootstrap signature. Note that the application key is available in memory for the Bootstrap to use in the decryption of the application in a further step. If a valid signature is detected on the Bootstrap file, the boot ROM code jumps to the Bootstrap in internal memory and begins the execution of the Bootstrap. The Bootstrap then validates the signature of the encrypted application file. The Bootstrap then moves forward to the next step. Before decrypting the application into the DRAM, we recommend using one or both of the following security aspects of the Microchip MPU device. The first one that is available on all our devices is a data bus scrambling process, which scrambles the data bus on the fly. The second would be to encrypt the DRAM interface using a key either generated from the true random number generator or can use the customer key from the OTP memory. So the reason for this, if you just loaded an a decrypted application in a DRAM, it would then be exposed to the world if you have external memory. So having done all the work to encrypt your Bootstrap and encrypt your application, it makes no sense to leave it in the clear in DRAM. The Bootstrap then reads the application out of the non-volatile memory, decrypts it, and loads it into the external DRAM. The Bootstrap will then jump to the application and begin the execution. In this particular case, we show the application as being both the OS loader, the OS, and the end user application. This process can be repeated many times. So if you want individual encryption for the individual aspects of the product, i.e. you want a different encryption for the OS versus the application, this is all provided through the the secure boot provisioning with the secure Samba application. Again, like I mentioned before, this would be repeated if we were to have independent encryptions for the different applications. So at this point, the application is now running in the DRAM. Being as we encrypted or scrambled the DRAM bus, the application is still protected from prying eyes and looking into seeing what the application does or how it does it. Now you actually have a hardware-rooted trust implemented in the platform, which can be used to continue the security of the process by secure updates as well as additional security features on board. In our case, the secure provisioning and secure boot they're free. They're relatively low touch in both the engineering effort and in the factory. By having encrypted Bootstrap and encrypted applications, you can protect your production line from mishandling and or misuse of the programming tools. Without having secure boot, it's sort of like having a house with a poor foundation. It's not structurally sound. As is, a system without secure boot is weak and susceptible to attack, no matter what the upper level security has been instituted. As a reminder, this is a part one of a three-part series. The other two parts of the series are secure provisioning, securing the production line, and the third one is MPU and their security features. Note, this is being recorded and is available will be available on the Microchip's Shields Up webpage, including the presentation as well as other security presentations. I I encourage you all to go look at the other presentations from the FPGA guys, SPG, the Computer Products Group. All the previous 8 sessions are available online, and they have a lot of good information, especially if you're not familiar with the SPG group's security processes and the FPGA. Thank you for your attendance. As mentioned before, this will be available online.